check this out. I have this tool. Okay, so that is a fogger. The idea is that you input some liquid in here, okay, and then it kind of makes it evaporate and it creates a fog. That's done. That's usually used in for the parties, for like any events, and also for filming cinematography like sequence, because that creates more dramatic effect. Check this out. So most importantly, it has like the button over here in the control, and not like it's going to help you understand something better, probably not, but it's going to create a more dramatic environment here. Okay, cool. By the way, today I prepared like dope content for you, like 100% dopeness guaranteed today. Definitely stay tuned. It'll be amazing. Today we're talking about heap-based allocation. Let's go. Okay, so here are my notes. Okay, heap. Okay, what is a heap? Heap is a region of storage in which subblocks can be allocated and deallocated at arbitrary times. Okay, so what does arbitrary times mean? That basically means that it can be done at any time. That's being compared, that's being opposed to stack. Okay, so when you have a stack, it's very clear when something is being allocated on top of the stack. When some amount of memory is being pushed on top of the stack. That usually happens when you have a recursive call, when you have a function, and there is some other function which is being called. Okay, and at that moment when the function is being called, that new frame is being pushed on top of the stack, and that's when some amount of memory is being allocated on the stack. With heap-based allocation, though, you can do it at any time. You can allocate the data at any time, and you can deallocate the data, which means you can free that up. So allocate means that you're basically saying, hey, operating system like Windows or Mac, can you please give me that memory? I actually need that. The memory, the system gives it to you, and it promises promises not to touch it, not to do anything with this. However, when it's being deallocated, it's basically the opposite, vice versa. So you're giving it back to the system. You're saying, hey, like, thank you so much, we appreciate that. I'm done using this. Now you can use it for any other purpose, or for example, if somebody else is asking, some other process, some other program, some other code is asking for that memory, you can please go ahead and give it to them. That's the idea. So when we're talking about static and stack-based allocation, that's since again the system is managing this, right? You're not doing, you kind of like your desire, your wishes, you have nothing to do with that. System decides when to allocate, when to deallocate. So it allocate, for example, with stack-based allocation, the simplest example. When a function calls another function, okay, so something is being allocated on the stack, and then when that function is when the code exits the function, when the compiler finished processing their code, when that function returns something back to, let's say, the main method, at that moment of time, that memory is being deallocated, which means that the amount of memory is being put back into the storage, it's being returned to the system. Okay, with the heap though, again, everything is completely up to you. Technically, in Java, unfortunately, there is not that much you can do with this. If anything, honestly, I think there are a couple of functions, very, very advanced things like you can do with that, but I never use them. I've seen them, but I didn't use them. In C, C++, or like, not C# though, but C, C++, C++, it's just like super flexible memory-wise, which is good and bad, right? So it's good because you have the full control of it, and that's why if you know what you're doing, you can just do crazy stuff. And I've done it like myself. I remember at TI, we were doing like crazy, absolutely like insane things with memory allocation. But It's bad because like if you once you make a tiny mistake, you can screw everything up, like absolutely everything. So you can actually change something in the location of memory which is not supposed to be changed at all ever, and your machine may not even turn on. I remember like on my Mac, at some point I went to, I'm not sure if I told you before, but I changed the ownership of the root directory. No, hold on. Yeah, of the root directory, yes. I changed the ownership. I changed that from root to my personal like user, and then that you're not supposed to be doing that, and it actually didn't allow me to do that. But then I found some hack. It was also having something to do with the memory space. So I kind of hacked it. Thought that I kind of like I know what I'm doing, but I didn't. And what happened was that so everything was working. I got the ownership. I got the membership access. I got the access to the data I needed. But then when I restarted the computer, which is kind of technically considered to be the root user, was trying to access some of the, some resources, and it was not able to because those resources belong to me, belong to the user, not to the computer. Kind of. I mean, I'm simplifying a lot of things. But anyway, so I was not able to restart the computer. So everything worked until the first time I rebooted the machine. And I had to basically like wipe the whole thing out. And kind of like I remember like when I pushed that enter button, like because it asked me a couple of times if I'm sure like I should be doing that. And when I pushed the enter last time, I actually thought about maybe I've done something wrong, and that was the case. Anyway, hold on, not as dramatic as it should be. 1 second. Let's put some drama. Now we're ready. Deallocated arbitrary times. Okay, so we got that. Okay. Heaps are required for fully dynamically allocated pieces of linked data structures for objects like fully general character strings, lists, and sets, whose size, and that's the key. Okay, so now like pay attention to what I will be saying. Whose size may change as a result of an assignment, statement, or other update operation. Okay, cool. Yeah, that's the idea. So internal fragmentation occurs when storage management external unused space composed of multiple blocks and require a lot of space. Okay, so internal and external fragmentation. Okay, so what's that about? We'll be talking about internal, external fragmentations, and then we'll be talking about the fit, best fit, first fit. Okay, so here's an idea. Imagine that you have some amount of heap. So imagine that you have this. Okay, so imagine that's your heap. Okay, and now the question is, so let's say for example this block is used. Okay, now so now hold on, let's say, okay, yeah, so let's say this block is used. Okay, this block is used. Okay, so they do not have to be the same size, right? And let's say this block is used as well. Okay, which means you have some amount of space available. Okay, that's available, and that's available. Okay, so the question is like, how do you create them? At what addresses you create them? Those blocks which you give to the user, and how do you recreate them? Okay, so for example, again. let's say you create this block, and then you create this block, give it to the user, you create this block, give it to the user, you create this block, give it to the user, and then for example the user says like, hey, I don't need this anymore, okay, and then it gives it back to you. Okay, so what do you do? Like, do you actually move this block over here? Okay, so do you move this block over here, or you just let it be where it currently is? Okay, or maybe do you move like this block over here as well? Okay, because the idea is that, for example, if you don't move this block, if you just leave this space to be empty, then maybe, I don't know, half a second later, a user may be asking for some other block, some other like memory space, which will be that big. Oh, sorry. Which will be that big. Okay, so you see, that's not going to fit in this space, and unfortunately, in this case, again, like we'll probably have to like allocate it somewhere here, and this space will be empty. So although it may seem like a pretty easy task to manage like everything in the heap, unfortunately it's not that easy, unfortunately. Okay, so that's why like there are so many issues in the compiling operating system. Like all the developers have to fight with that. How do you do like the most efficient way? Okay, again, so let's say again you created this block, this block, this block. You gave them all to the users. Then the user said like, I don't need this block anymore. Okay, so and then if you move this guy, okay, so if you move this guy over here, then in this case you can, if the user comes back asking for this amount of memory, you can actually place it over here. You'll have enough space to fit that in. Okay, so that kind of stuff. Anyway, yeah, internal external fragmentation. Okay, internal one occurs when a storage management algorithm allocates a block that is larger than required to hold a given object. Okay, so a storage management algorithm, which means operating system, allocates more memory, allocates a block which is bigger than the user is asking. Okay, so in this case, again, you allocating that much memory, and then so it's allocating like huge amount of memory and gives you like some portion of it. So that's where internal fragmentation happens. So that's internal fragmentation. Bum, bum, bum. Okay, so what happens is the extra space remains unused. Okay. External fragmentation occurs when the blocks that have been assigned to active objects are scattered through the heap in such a way that the remaining unused space is composed of multiple blocks. Am I recording? Yes. Is composed of multiple blocks. Okay. Okay, yeah. So there may be quite a lot of free space, but no piece of it is large enough to satisfy some future requests. Okay. Then maybe. Okay, so again. Let's say that's your heap. Okay, so that's much memory you have for the heap. And then okay, so you allocated this and gave it to the user, you allocated this, give it to the user, you allocated this, give it to the user. But then user comes in and he's saying like, hey, like I want like this much. Okay, so it almost fits here, but it doesn't, and it almost fits here, and it doesn't. Okay, so that's kind of a problem, right? And like, what do you do in this case? That's the question. Okay, now many storage management algorithms maintain a single linked list, okay, so-called the free list of heap blocks not currently in use. Okay, yeah, not currently used. Initially, the list contains a single block, right? Because like the entire heap is not used, right? So you have only one block, only one pointer. The entire heap is not used, so there is only one block, which is the entire heap, comprising the entire heap. The entire heap. Okay. At each allocation request, the algorithm searches the list for a block of appropriate size. Okay. Yeah. Okay, now there are two methods. Okay, so with a first fit algorithm, okay, with the first fit algorithm, we select the first block on the list that is large enough to satisfy the request. Okay. For example, let me show you this. Again, let me draw the same picture. So that's your heap. Let's say this is used. Okay. Let's say this is used. Okay, let's say this is used as well. Okay, so there is some space in the middle. Let's say this is used and there is no space in the middle. Okay, and let's say this is used as well. Okay. Yeah. Okay, so again, that's used, that's used, that's used, that's used. Ah no, that's okay, that's used, sorry. That's used. Okay. That's used and that's used. Okay, cool. So, and then the user is asking for this much memory. This much. Okay. So with the first fit algorithm, with the first fit approach, what heap management system is going to do, it's going to sort. Oh yeah, by the way, so we're talking about the free list. Okay. So what is a free list? Free list is a linked list. Okay. Of pointers. So here's how it's gonna work. So that's a pointer. No. That's a pointer. That's a pointer. Okay. So they point to the memory spaces which are available, and that's a linked list, right? So okay, so there's the first node, there's the second node, there's the third node. Okay, and that's probably null. Okay, that points to null. So basically, that point is the memory address which contains the free memory. Okay. Now the question is how much free memory. That's basically you can calculate by using another list. There is also sometimes there is either another list which contains. There is either another list which contains the memory addresses where the memory is being used, it's given to the user. So that's one way. Or another approach is to, in this list, to keep track of how much memory is being free. Okay. So also there is not that big of a difference between them, but basically, anyway, the system which has that free list knows how much memory available you have. Okay, is it like 1 megabyte, 2 megabyte, is it 2 gigabytes? So like how big is this? Okay, now with the first fit, what's happening is this. Algorithm is going to decide where to place this much memory, and with the first fit approach, it's going to place in the first window where you have enough memory. Okay, for example, in this case, that's going to be placed over here. Okay, although look at how big it is compared to this small chunk of memory. That would be probably a lot better if we actually piece it over here, if we insert it over there. But again, when you just have a list, right, how do you know where this is located? Maybe it's actually, I don't know, like 20,000 times pointers like later, and you have to traverse huge amount of things, right? So how do you know that? With the first fit approach, it's basically like, hey, I'm going to traverse this list, okay? And once I find some chunk of memory which is enough, which means which has the same amount of memory or larger than I'm looking for, I'm going to stop searching. I'm going to insert I'm going to allocate that memory. Okay, I'm hoping I'm explaining that well. Yeah, so that's the first fit, okay? And the opposite of that would be the best fit, okay? So that's the first fit, yes, but it's not the best. The best fit would be probably over here, right? Where you're basically looking for the amount of memory which is bigger than required, but as close to the one which is required. Okay, that will be the best fit, and that's the first fit. Okay. That's the best fit. Yeah, so that's the first. And with the best fit algorithm, we search the list we search the list to find the smallest block that is large enough than required. Then we divide. Yeah, than required. Okay, hold on. Yes. Okay, than required. Okay. In either case, if the chosen block is significantly larger than required, then we divide it into and return the unneeded portion to where? To the free list. Okay, so one more time. Okay, if I draw this thing, so let's say again, if we use the first fit approach. Okay, so in this case, this chunk of memory will be fitted over here, and kind of this pointer doesn't point to the free memory anymore. Okay, and that's why that has to be deleted, and another one has to be created, which will be somewhere over here. Okay, yeah. So that will be the new pointer. That will be the new member of that list, and this guy will, and this guy will go away. Okay, yeah. So there'll be new pointer, a new element of the free list. Okay, which will point to the new memory address which contains free space. Yeah. Okay. Now the question is, what happens when we deallocate? When we deallocate, when we a block of memory, we return it to the free list. Okay. We check to see whether either or both of the physically adjacent blocks are free. If so, now a word which I can pronounce, coalesce them. Basically combine them. Okay, what does that mean? Let's say there are two blocks of memory which are physically adjacent to each other. Okay, these two. Okay, they're physically adjacent to each other. And let's say you want to, I don't know, well, no, not these two. Let's say there are two blocks of memory which are adjacent to each other. One of them is free, the other one is allocated. Okay. Now let's say we are deallocating this block. Okay. So what happens is that the program returns back to the system, and now instead of creating like one more pointer over here, right? We need to create, so instead of just creating one more pointer in the free list, we need to create this one, and we need to delete this guy. Why? Because that actually, since these two blocks are adjacent to each other, we're not creating the second block, we're just increasing the size of this block. Okay? Hope it makes sense. So now the question is, like, which one works better, right? So unfortunately, there is no answer. Not that easy to answer that. So intuitively, you would think that the best fit approach is better, right? For serving certain large blocks of requests. Okay. At the same time, it is higher. It has higher allocation cost than the first fit algorithm. Why? Because it must always search the entire list, and it tends to result in large number of very small left over blocks. Okay, so basically it's a classic trade-off. Okay, so when we're talking about first fit, how can it be better? It's better because once you you don't have to search that much time, right? So once you find the block of memory which is big enough, you just insert it there, and that's it, and you give up. This is the first fit. So why is it bad though? It's because you just create. It's possible that there is you just creating so many like super small chunks of memory which you cannot fit in which you cannot fit anything. Okay, so it's quicker, but it's quicker, but it's not as efficient. Okay, if you're doing the best fit in this case, you always have to, not like in the worst case scenario, but you always have to traverse the entire list in order to find the best one, and so you have to spend quite a bit of time every time there is a request for memory allocation. Okay. Yeah. So basically, yeah. Okay, hold on. One more thing. Yeah. No, that's it. Sorry. Yeah. So how does it happen in C? Okay, in C there is a function called memlock, which stands for memory allocation. Okay, so basically it's saying something like this: int a is equal to memlock, and then you need to provide a number of bytes, specifically bytes, let's say 50, and that returns your pointer to that. And then you say free A, and that's how you do deallocation. So again, when you do memlock in the heap, they are requesting 50 bytes of consecutive data, okay, 50 bytes, and returns you the pointer to that data, and then you can just put something in there. Okay, and then when you say free A, that means like you basically saying system, hey, like can you please give, like I'm giving that back to you, that's your 50 bytes, I don't need that anymore, thank you so much. Okay, cool, so let's stop here. I hope you guys enjoyed this class. Good luck on the midterm number 2, right? So you need to learn everything which was from the first midterm up until today, including what we covered today. Hope you guys staying safe. I hope the coronavirus is not impacting you that much. I'll see you guys later. Bye bye.